Sorry, Melanie. So we'll have Emma come up first. See if we can get your Zoom into just on your problem.
So I number 20, and it's the cube root of 64x to the third y over 4x to the negative third times y. So the cube root of 64 and x would be 4x, and then you get the cube root of y at the top. And then x to the negative third will go up top because it's negative, so x times x to the third. And then you have 4y left on the bottom, and the 4's cancel out, so you're left with x to the fourth cube root of y over y.
Does anyone have questions on number 20? And I can work out, but I'll make sure that you all get it. That'll be, I have it like super zoomed in. And zoomed for you. There we go.
Alright, thank you.
So number 24 was the cube root of x to the fourth times square root of x to the fifth, and it's all multiplied by negative 2. And first you have to change the fraction to exponent form, and then you have to do x4 to the third times x to the 5 over 2, and then this is all multiplied by exponent of negative 2. And then you have to distribute the negative 2, so you get x to the negative 8 to the third times x to the negative fifth. And then you have to move the values to the denominator because of the negative exponents. And it becomes 1 over x to the 8 to the fifth times x to the fifth. And then you have to add the exponents and set the fraction denominators equal to each other. So you do 8 over third plus 5 over 1, and you have to multiply the 5 and the 1 by 3. So you get 8 to the third, 8 over 3 plus 5 over 3 equals 23 over 3, and then your final answer is 1 over x to the 23rd, 23 over 3.
Just want to keep that there for a minute. Thanks, Jeff. So just putting this one back up there. Sometimes when you're working through problems, it's easier to work through them as an exponent that's a fraction instead of keeping them in square root form, which you can keep it in square root form, but sometimes looking at it as a fraction makes it a little easier because then you're getting it out of that radical. And fractions are sometimes easier to simplify than it is in radical form. So changing the radical into a fraction, remember the power, the 4, stays in the numerator. The number on the little radical part goes to the denominator. So switching that into the radical form and then distributing the negative 2 through makes it simplify a little easier. I worked through it both ways, so I just think that this way might be a little easier to kind of look at and get those fractions to simplify. So that final answer should be 1 over x to the 23 thirds. The answers were on the back, so make sure you are checking those answers that are on the back there. So are there other questions from the homework that you wanted to go over, work through? Melanie?
On number 10.
Yeah. So number 10 is 54 64ths. And then that's all to the exponent of 1/3. And the directions in this group just said to simplify the expression using properties of the exponents or properties of radicals and rational exponents. So, Melanie, what's the first thing you thought of doing with that 1/3 power? Yeah, so distribute to each piece of those. So that gives us 54 to the 1/3 over 64 to the 1/3. How would you write an exponent of 1/3? How else could we write it? Because you can't really do anything with it right now as it's 1/3. So how else could we write the exponent of 1/3? Jillian? Right, we could make it a cube root. So we could look at this as the cube root of 54 and the cube root of 64. So your common power sheet. One of those two numbers is a perfect cube. Julian, which one of those two numbers is a perfect cube?
64.
The 64. So the cube root of 64 becomes 4. So that's really nice because it is a perfect cube. It changes to the number 4. However, 54 is not, but we can at least break it down by using that common power sheet because one of those numbers from the common power sheet goes into 54. So we're going to break down 54 into two perfect cubes, or one perfect cube and then whatever is left over. Here, do you know what goes into 54 that would be a perfect cube?
Oh, I think I have 4.
Hmm.
Numbers?
Number 10. So the numerator of 10. What can we break down 54 into?
I did, 27 and 2.
Yeah, perfect. 27 and 2. And the reason you chose 27 is because the cube root of 27 is?
3.
3. Yeah, so then that becomes 3. We still have the cube root of 2, and then that's all over 4. So both of those have the 1/3 exponent, so distributing that through, changing it to a cube root because we're dealing with numbers, we want to try and break down that power. Other questions? Maggie. Say it again. Oh, you only had to go up through 26. Jill. You said 12, right? So number 12 has the 5th root of 5 and the 5th root of 27. This is a good one to look at too. So in number 12, we still want to simplify, but we have a radical in the denominator, and in that radical, we have to make sure the denominator is rationalized. So we have to figure out a number to multiply the denominator by, so that when I take 27 and that number, our end result is a perfect fifth. So we need to have 27 times some number to get a perfect fifth over here. Connor?
Multiply by 9, get 243.
So he said if you multiply it by 9, you get 243. So I would suggest using that common power sheet and looking for this number first. Like looking at the common powers and saying, all right, if I have the fifth root, or the power of 5, what are the powers of 5 that we can try and get to? So 243 is one of the powers of 5. How can I get to that number if I have 27? Well, 27 times 9 gives us 243. So whatever you do to the top of a fraction, you have to do the same thing, or whatever you do to the bottom, you have to do the same thing to the top. So Connor, on the top we have the fifth root of 45. And then the whole reason that we chose to multiply by the fifth root of 9 is because once you multiply them, Connor, the fifth root of 243 just becomes 3. And that's called rationalizing the denominator. So once we get that number that becomes a perfect fifth, that's what it's called, a perfect fifth, meaning we can take the fifth root of it. We want to change that number into the whole value, because that's when a denominator is simplified or rationalized. So we get the fifth root of 49 and then divided by 3. Other questions? Jordan. 21. All right, so 21, we have x to the 5th times x to the square root of 3. So if you have the same variable, what do you do with the exponents? You add them. So how would you add those together, Julian? Yeah, you would just keep it as 5 plus the square root of 3. Joel, I'm betting you made it like you probably thought it was much more difficult than that because all the other problems were a couple extra steps. That's the only thing you can do with that problem. You can't actually add 5 and the square root of 3 together. I don't want you to like make it a decimal because we don't want to have decimal values. But the property, because you're multiplying, you're adding the exponents, but there really isn't anything to do when you're adding them besides put the plus sign in there. So that's as far as that one can go. You can't do anything else with it. Others? So I would like you to pass forward both homework assignments. So I'd like to look at the book because I didn't get to see that yesterday, the book homework, and then also the worksheet. Today we're going to just work through a couple more problems, try and wrap up this section. On Monday, we'll review sections 4-5, which was the rationalizing the denominator, so like 1 divided by 3 plus the square root of 2. Section 6-1 and 6-2. 6-1 and 6-2 are pretty much identical, working with those exponents, the rational exponents and those properties. So we'll review that on Monday for your quiz on Tuesday. In your packet, if you can turn to section 6-2 again. We're going to go down to example 5. And work through some problems involving variables, which you already did some problems involving variables. But we'll also work through some variables where you've got a radical in the denominator, just like a number in the denominator. So if you look at letter A, we have the 5th root of 32 times x to the 15th. The directions say to simplify, and then it says assume all variables are positive. That part up there is given to you. There we go. Because if you have a negative number that you plugged in for a variable, and you have a square root, you can't take a square root of a negative number. Or if we have a 4th root, we can't take a 4th root of a negative number. So that information is given to keep the variables positive so that that number underneath, if we did have a number underneath for the variable, it would remain a positive value. So that information is there for that specific piece to make sure that when we take an even root, it becomes a positive value. So in A, we have the 5th root of 32 and then x to the 15th. So when you're thinking about this, and you don't have to write it like this, technically, you're looking at these as individual pieces. You're looking at it as the 5th root of 32. You're looking at it as the 5th root of x to the 15th. You don't need to separate it, but sometimes looking at them as separate parts helps work through the problem. So the common power sheet, if that's on your desk, it's a really good thing for you to have to reference. Gavin, what is the 5th root of 32? Oh, sorry, you don't have yours up yet. Say again? 2, yeah. So the 5th root of 32 is 2. It's a perfect fifth. Gavin, do you know what you would do with the 5th root of the square root of x to the 15th? Anybody have an idea what you would do with that? How do you take the 5th root of x to the 15th? Connor? Yeah, that's what you're doing. You're taking 15 divided by 5. Because if we rewrite this, so right now it's a radical, but if we write it as a fraction, this really means x to the 15 divided by 5. So when you have a radical, the number outside is the denominator, writing it as a fraction. The number with the exponent is the numerator. So you're really taking those exponents and dividing them. Because technically we could write it as a fractional exponent, which means we would divide. So Connor, 15 divided by 5 is just 3. So that becomes 2x cubed. So with radicals, you are really dividing because we could write it as a division problem. That's what a fraction is. A fraction is another way to write division. So if you look at letter B, we have 36m to the 4th, n to the 10th, and then that's all to the 1/2 power. Maggie, if something's to the 1/2 power, what does that mean? It's square rooted, yeah. So the 1/2 power is another way of saying it's square rooted. So we're taking the square root of 36, the square root of m to the 4th, the square root of n to the 10th. When you say square root, remember really there's a little 2 sitting here because it was the 1/2 power. So technically you can put a little 2 there. Made you think that there's a number there. So Maggie, the square root of 36 is 6. The square root of m to the 4th is, and the square root of n to the 10th is n to the 5th. So all those powers, you're dividing the power by the number sitting on the radical, by the root. All right, so let's look at letter C. Instead of multiplying now, we have division underneath a radical. So we can really look at this as the cube root of a to the 9th and the cube root of b to the 6th. So still dividing. Melanie, what would that make?
What?
So what would the cube root of a to the 9th make?
A to the 9.
Yep, what is 9 over 3?
3.
Yeah. So the top one becomes a to the 9 over 3, which is just a cubed. Melanie, how about the bottom one?
B squared.
Yeah, because this is b to the 6 over 3, which is b squared. Any questions so far? So there's always that exception that doesn't work as nicely, and that would be letter D. So letter D, we have the cube root of x over y to the 8th. And I'm going to just rewrite this, separating them. So the cube root of x, the cube root of y to the 8th. Just like we did with letter C. So what's wrong with the denominator? You know, everything's wrong with it. It's a fraction to begin with, so therefore it's wrong. But what's wrong with the denominator? It's not rationalized. What happens when you take 8 divided by 3? Yeah, it doesn't go in evenly. So 8 divided by 3 doesn't work as nice as 6 divided by 3. 6 divided by 3 is 2. But 8 divided by 3 doesn't work so nicely. So we need to force it to work nicely. What do you think you could do to make it work so that it does divide? Connor, what do you think?
Multiply by y again so it becomes
Yeah, very good. So we want this y to be a 9 so that we can divide it. Well, you're allowed to do anything to a fraction as long as you do the same thing to the bottom and the top. So we're going to multiply this by the cube root of y to the 1st so that it becomes 9. Because I have 8, we just need an extra one to make it 9. And again, you're allowed to do that as long as you do the same thing to the top and bottom of the fraction. So with algebra, an equation, you're allowed to do anything to the left and the right of the equation. A fraction, you're allowed to do anything as long as you do the same thing to the top and bottom of it. So on the top of this fraction now, we have the cube root of x times the cube root of y. Well, we can just write that underneath one cube root because they're both cube roots. They're the same radical. So we can place them under 1. And then on the bottom, we have 8. Here's another one to give us 9. So that's how the bottom would look. And Connor, now that we have the cube root of y to the 9th, that would become,
y cubed.
yeah, now it's y cubed. So that's still rationalizing the denominator, but we rationalized it with a letter, a variable, instead of a number. So we added an extra 9 down there, or an extra y down there, to make it 9 so that we could then divide it. Questions? this, there are a couple more examples on the next page. Lots of examples in this section. It's a pretty large section. Lots of different options to look at. So the last three examples, and then there's just like a couple of review problems underneath. One is to add or subtract with variables. So yesterday we added or subtracted with numbers underneath a radical, and now we have variables to work with. And as long as your variable is the same and it has the same power, then you're allowed to add and subtract them. So if you look at letter A, we have the fifth root, bless you, of y. We have the fifth root of y. So that's a like term. You just subtract the numbers in front. So 10 minus 6 gives us 4, and then we have the fifth root of y. So as long as the power and the letter are the same, or the root, that's the square root part, whatever that root is the same, then you're allowed to add those together. They're like terms. So looking at the next one, we have a squared b to the 1/4, a squared b to the 1/4. It's addition, so we can add the numbers in front. The variables just tag along for the ride, so they're not changing. It's still a squared b to the 1/4, because you're just adding the numbers in front. Just like that was an x. If it was 3x plus 4x, we would write 7x. Here's the exception. Letter C isn't as nice as A and B. Because in letter C, we have the cube root of 5s to the 4th. We have the cube root of 40s. They're not like terms anymore. Yes, they're both cube roots, so that's good. The root part is the same. But the number underneath is not the same. So we're going to have to try and force it to become the same value by trying to break down the square root or the cube root. So if you look at this first part here, I'm going to ignore the 10 for a minute and just work on this cube root. We have the cube root of 5 and the cube root of s to the 4th. And I probably should put 5's and s's in the same problem. So can you do anything with the cube root of 5? Can that part be broken down? No. But let's look at the cube root of s to the 4th. How can we break that down? Odette?
S cube root of s.
Yeah. So if there's 4 s's in here, you could say that you have s cubed with an extra s. So if there's 4, we can break it down as s cubed, and then an extra s because 3 plus 1 still makes 4. So that means this one here goes outside and just becomes s. And then we still have the cube root of that other s that remains inside because it doesn't divide out. So the first one divides out because we have 3 divided by 3. So that divides out and goes outside. But the other one remains inside, that s to the first that's left over. And inside with it is also that 5 because that was left over. And then I'm going to bring that 10 down and place it in front. So we have 10s and then the cube root of 5s. That's what our first term now says. Initially it said 10, the cube root of 5s to the 4th. Well, now it's changed because we've simplified the radical. So looking at the next one, there's a minus sign, so we have another part here. We're going to try and do the exact same thing with this one. So we have the cube root of 40, and we have the cube root of s. Try and squeeze that in. Starting with the number, is there a perfect cube that we can use to break down the cube root of 40? So looking at that common power sheet, any of those numbers, Gavin, what would go into 40? 8 and 5. So we could change 40 into the cube root of 8 and the cube root of 5. Gavin, the cube root of 8 becomes 2. So the cube root of 8 is now 2. We still have the cube root of 5 and then just the s. That s was initially in the problem and it's just an s to the first power. So now we're subtracting 2. The s that was here goes outside with the s, so it was initially there. I'm just bringing it back down. It's attached to the 2 that we brought out. And now we have the cube root of 5x. So it's like we're simplifying each piece of that problem, but our end goal was to get it to have the same like term part. That's all of the stuff after the numbers. So once they're the same, then you can subtract the numbers in front. So 10 minus 2 gives us 8. And then we have s, and then the cube root of 5, and an s. So the like term part we had to make the same. We had to make those radicals become the same. Once they were the same, then we could subtract the numbers in front. Questions? So there are, I believe, 6 problems underneath here. Just with working with simplifying the expressions, trying to give a couple examples of the ones that we went over. The first one, we have the 4th root of a squared divided by b to the 6th. So you're really looking at the 4th root of a squared, the 4th root of b to the 6th. So this is that fraction where the denominator doesn't work nicely for us because you can't take 6 divided by 4. But we need to rationalize the denominator so that we can do the division. So what would you multiply the denominator by so that b to the 6th divides nicely with the 4? Julia, what do you think? What do we multiply the denominator by? So how could I make this b to the 6th become a power that's divisible by 4? What could we multiply that by? And a power would be half. Yeah. So if we multiply that by b squared, so the reason we're picking a 2 is because when you add the exponents of the b's, 6 plus 2 gives us 8. So now we have the 4th root of b to the 8th. On the top, we have a squared, we have b squared. So Julia, what does the denominator become then, since we changed it to that b to the 8th? So if you have 8 and the 4 outside, what happens with those? Yeah, that becomes b squared, because this is now saying b to the 8/4. So the goal is to get a power that's divisible by that number, that root. So the 6 isn't divisible by 4, but we can multiply it by a b squared so that that number becomes an 8, which is divisible by 4. So that's still rationalizing the denominator, but you're rationalizing with a variable. Questions? They're tricky to think about. There's a lot of different rules and properties that you have to think about with all these exponents. So letter B, we now have just a multiplication problem, but it has a lot of different variables. So you're looking at the cube root of 6, the cube root of x to the 4th, y to the 9th, z to the 14th. And really, that number on the radical is what you're dividing by. So you want that power to divide by the radical. So the x to the 4th, I could break down as a 3 and a 1. And the reason I'm picking a 3 is because I want it to be divisible by 3. Y to the 9th divides nicely. Z to the 14th doesn't. But we could make that a 12 and a 2. Because 12 is divisible by 3. And 12 plus 2 still makes 14. I'm just kind of splitting them up so that we can then simplify it. So we have the cube root of 6. Can we take anything with the cube root of 6? No. So So that's going to stay the cube root of 6. The next one with the x's, we have the cube root of x cubed and x. So what would that become? Yep, so one x goes outside, the other x stays inside. How about the cube root of y to the 9th? Good, that's y cubed. And then the cube root of z to the 12th and z squared. And then the z squared. So the one that divides nicely, you're going to pull out and actually divide that. So 12 divided by 3 is 4. So that one divides nicely, you're pulling that out. If it doesn't divide nicely, it just stays underneath. So see if you can do letter C, kind of following the exact same step. I'm going to write my letter C underneath here. But try and do that same process. We just have A, B, and C instead of X, Y, and Z. So I have my variables divided up, or split up, I should say, so that the first variable is the power that will divide. The second variable is whatever is left over. So 8 is 6 and 2. The 14 is the 12 and the 2. And the c to the 5th, the 5 is the 3 and the 2. So when we simplify those, Brandon, what do you get? So the 4 we can't simplify. What happens with the a's, Brandon? So just looking at the a to the 6th part here. So 6 divided by 2 becomes, or 6 divided by 3 becomes, yep, so a 2 comes out and the other stays in. So this part you're taking 6 divided by 3. And then Brandon, the next one we have 12 divided by 3. E to the 4th. B squared inside. And then the last one, 3 divided by 3. And then C squared inside. So the first piece comes out. The leftover piece stays inside. Questions? Why don't you look at letter F? I think these are the hard ones because there's a lot going on with these. So letter F, we have 7, the cube root of 2a to the 5th. We're subtracting a and the cube root of 128a squared. This over. So I'm looking at letter F here. So in order to subtract them, we need to make that radical become the same. So then they can be subtracted. So it's the same as the one we just did, except there are 2 of them, and we're trying to subtract both of them. So there's the 7 outside. And then I broke up the a to the 5th into a cubed and a squared so that it divides. So we would have the a come out. So now I have 7a. And then we have the cube root of 2a squared. So a to the third divided by 3 comes out as a. And then looking at the next one, we have a minus a, and then the cube root of 128a squared. Mackenzie Myers, do you know how 128 would break down?
Break down to
64 and 2. So what would that become then?
it becomes 4
And then a squared. So the number here, the 28, 128 breaks down. But a squared does not because it's less than the power outside, so it just stays underneath. So the goal is to have the like term part, and that's everything after the number. So once they're identical, then you can subtract 7 minus 4, which is 3. We have an a, and then the cube root of 2a squared. As I said on Monday, this is definitely a challenging section because of all of the rules and properties and trying to break down radicals that are no longer just a square root. So the worksheet here is a combination of 6.1 and 6.2. The back of it, the last 6 problems are more 6.2. The front of it is kind of like a little bit of mix of both of those. I'll send out an answer sheet to remind so that you have the solutions to these. We'd look at 10, 20, and 23. There's still a handful of you to get a presentation problem. So 10, 20, 23, anybody interested? Okay, so Tatum, how about 10? Garrett, 23, and Will, Garrett 20, Will 23.